reaction.
Hello and welcome to this video on dynamic equilibrium. What we're going to look at today is just the definition of equilibrium, how we can show it on a graph, and how we can link it to our idea of a rate of reaction. This is suitable for the C8 module in GCSE, AQA, any rates GCSE module, as well as maybe a little refresher for a Year 12 student. So let's first look at how we'd show this in a reaction. Typically, we're used to looking at reactions where we have A plus B as our reactants and a single arrowhead showing that we're going to our product C. What we introduced in the last video was the idea that a reaction could be reversible and it could go back the other way. So we could have A and B as our reactants, making C as a product, and then as a second reaction we could have C going to A plus B. So if I show those two scenarios, obviously scenario 1 from this reaction, A plus B going to C, that's just showing it in the conventional way, and then obviously the reverse of that would be C going to A plus B as our products in that scenario. So this here obviously means that the reaction is reversible, and what we're looking at today is the attainment of equilibrium. So I've got this demonstration for you here on my ironing board. It's very homemade, and we've got A and B here, and the concentration in this demonstration is shown by the water. So this trough is full of water at the moment, showing that we've got our concentration is made entirely up of A and B. They are our reactants. C, our product in the forward reaction, is empty. There's none of C present in our vessel, and I've shown the reversible symbol showing that this is going both ways. I've got two identical cups here, and what we're going to do is treat these as our rate of reaction. So when the cup's full, that's showing that from A and B to C our rate is maximum. That's as much water as we're going to get in this demonstration. And initially, obviously, there's no water in here. That will be empty. So C to A plus B, that's going to have no rate at all. So let's just see what happens and how rate is changing over time. So when I start off, as I said, maximum rate of forward reaction and no rate of reverse. However, I've now produced some of C. A and B obviously still vastly in the majority. But what this means is at the second time, I've got the tiniest amount of rate, just a drop. Obviously still the predominant rate is forward from A plus B going to C. So I pour those away, carry on with this process a few more times. And what I see fairly quickly in this case is a rate of reverse reaction is starting to build up. C is starting to form A and B again. We can see it there in that cup. The rate of forward reaction still higher, but on the decline. It's decreasing. So if we show this on a graph of rate against time, what we've got is in scenario 1, we've started at maximum rate. So that's A plus B going to C. We had a full cup of water there. And my rate is as high as it could be. But it has then come down. If we're calling this curve 1, in 2 we started at 0 rate of reaction down here. So this is the reverse reaction, C going to A plus B. And that curve is just coming up there. It's starting, as we can see, to increase. The rate of that curve is starting to come up. So let's investigate what happens as I progress the reaction, as I carry on. So forward rate still higher. My predominant rate of reaction is still going from, as you see it, left to right. However, if I do this a few more times, we'll start to see something. Wonder what it is, given the title of the video. So if I now look here, rates are getting pretty close. So let's now compare these two rates. Almost there. Do it a few more times. And there we go. Obviously it's not a perfect experiment. And they are slightly different tubware boxes. But if I just have a look, the rates are now equal. Okay, so the rate of forward reaction, this one here, is equal to the rate of reverse reaction. There's actually pretty much the same volume of water in each of those cups. And what that means as we track this on our graph is that one has slowed down in this exponential shape and plateaued. We can now do this all day, all year. As I do this, there will be no change in the concentrations of A and B or C. So that will come to a point. I'm just going to draw it actually in the middle of the graph. And this one here will come up and join it. And at this point here, the rates of reaction, they are now equal. So this here is equilibrium. That is equilibrium, where the rate of forward reaction is equal to the rate of reverse reaction. And the concentration at this equilibrium point, if I look at the concentration, that will remain constant because I'm moving the same amount of water either way. So to sum up, dynamic equilibrium, rate of forward reaction is equal to the rate of reverse reaction. Now, this does not mean necessarily that the concentrations of A and B and C are the same. This point could be up and down this graph, and we could have differing concentrations. It would change, obviously, maybe the size of this tub in this demonstration, but with a forward and a reverse reaction, there will come a point in certain conditions where the rate of forward reaction and the rate of reverse is equal. So I hope this helps. Thanks very much for watching. As always, like, comment and subscribe, and we'll see you in the next one. Thanks very much.